Good morning, everybody in the lecture hall. Good morning, everybody on Zoom. Good morning or afternoon, everybody watching us from the future. So today we are going to continue working on constructing indices, in particular, make it scale. Now that we know how to do it on small scales with a small collection, we are just trying to build larger and larger indices on larger and larger collections. So this is where I left you with these tongue twister names for the techniques that we use. Does anybody remember what the name of the first technique was? BSBI, right? Blocked sort-based indexing. So you might remember that with this technique, what we do is we take the collection, which still fits on the disk. So the collection might be a few terabytes of data. And we split it in partitions. And we are going to process one partition at a time. We call it also a batch. And so the idea is that we process the batches one at a time, and then at the end, we will merge the resulting postings. We saw that for this method to work, we need to fit as many pairs of terms and documents in memory as possible. And this is the reason why we introduced term IDs. Just like we have document IDs, we have term IDs. And it means that these pairs of terms and documents are just pairs of integers, right? It's just the integer corresponding to the term and the integer corresponding to the documents. And since we have a lot of these pairs floating around in memory, then having them represented as two integers is going to eat up less space in memory. And we saw that we can allocate the term IDs corresponding to a term either as a first pass before we process the collection, we just scan once through the collection and create the term IDs, or we can create the term IDs on the fly. Every time we see a term for the first time, we just allocate the next available integer for it. So now that we have this, what we do is we go through the current batch of the collection, and for every token that we see in the collection, one by one, we create one of these pairs, term ID, document ID, and we fill the memory with them. We sort them, and then at the end of the batch, we write all of these pairs of term ID, document ID back to the disk, right? So at the end of every batch, what we have back to the disk is a huge number of term ID, document ID pairs. Then we do it for every batch. And at the end, we are going to read in parallel, kind of, all of these outputs of the batches, which are sorted sequences of pairs. And we are going to use the second part of the merge sort in order to go linearly at the same time through all of these lists of pairs in order to merge them into a single sorted list of pairs. Who is with me on that? Right? Okay, very good. And of course, that finally sorted list of pairs that we can convert easily into a standard inverted index, because that's exactly the same order as the postings. So now we have a few improvements. There was other people that kept improving, and actually some of you already mentioned a few ideas on how to improve some inefficiencies that we can fix. And this is why we have SPIMI, single pass in-memory indexing, that is a newer and better version of BSBI. So the idea is still the same, that we have these partitions of the collection and that we process the partitions one by one sequentially. However, there is going to be one first little change. Is that in every partition, instead of generating these term ID, document ID pairs, we are directly going to generate mini standard inverted indices, mini versions of this index just for the partition that you're currently working on, as if it were the whole collection. So it means that instead of doing that, you just process the tokens one by one. And every time you see a token, you add the corresponding term and posting into your structure. So you maintain a mini standard inverted index. Of course, at first, it's super small because let's say that's the first token we processed. So you just put the term here and the document ID here. That's your posting. And that's basically a ridiculously small index for just one token, right? But then you just go ahead and just consume the token. So maybe for that document, you look at the second token. That's a different term. So you add that term in here, but you just make sure to maintain this as the structure of a standard inverted index. It means that here, the terms should remain sorted. So whenever you insert a new term that you see, you always have to keep it sorted. So of course, it means it's not going to be appending at the end. It might be anywhere in the middle. And how do you, what is the logarithmic complexity for inserting a value in a tree that maintains the sorting? Logarithmic, exactly. Thank you. So that's in logarithmic time. Every time you add a term in logarithmic time. Who sees that we no longer need the term IDs? We don't need them anymore because now it's efficient. Every term is just going to be stored just once in this dictionary that is the standard that belongs to the standard inverted index. We no longer have any pairs anymore, right? The postings just have the document ID here and the term will be there. So we don't care anymore about term IDs. We don't bother to create them anymore. We just maintain this small standard inverted index. Here's, for example, now we look at a second document that again contains the yellow term. So we add the document ID and so on. Okay, so now we have a new term. We keep adding, right? Maybe it's a bad example that I put the terms in ascending order in here, but I should have put an example where you also insert them in the middle just for completeness. Okay. Now, question to you. So the algorithmic log complexity for adding a new term is logarithmic. What is the algorithmic complexity for adding a new document, a new posting in that structure? Knowing that the postings list must be sorted too, right? By document ID. What's the algorithmic complexity? Any ideas on Zoom? Okay. Does anybody know but just doesn't dare to tell me? Nobody. Okay, let's vote then. Let's just make a vote. Who thinks it's logarithmic? Because it's a sorted list, just like for the terms. Logarithmic? Nobody. Okay. Who thinks it's linear? Okay, yeah, not linear. That wouldn't be tractable, right? Who thinks it's O of 1 constant? I see a few raised hands. Yes, very courageous. And you're correct about it. This is indeed O of 1. Can anybody tell me why it's O of 1 to add posting like here? On Zoom? So here's why. It's O of 1 because the document IDs are just created by increasing an integer. Every time we see a new document, we just allocate the next available integer. So since we have a batch of the collection with documents, and we process the documents sequentially, I'm going to process document 1, and then document 2, and then document 3, and then document 4. So let's say I'm processing document 4. It means that I'll have already the postings with 1, 2, 3 for document IDs 1, 2, 3, they're already in there. And now I have to add 4 to all the places that there is a term in my document. Do you agree that this is just an append operation? I'm just appending 4 to the posting list, and that's it. I don't have anything to sort. I don't have to insert it anywhere. Just appending to the posting list for which there is a term in my document. Who agrees? Right? Okay, so this is highly efficient because the fact that we generate the document IDs on the fly just by increasing integers makes it very efficient. So the only part that requires a bit of sorting and maintaining the order is the dictionary on the left with the terms. Okay, so, okay. And then, of course, we need to sort by term. But again, this slide, maybe I redo it. It's a bit misleading because it looks like now we just create the posting list and then we sort by term. But you know that we actually do it on the fly. We don't just sort at the end. We just keep it in a sorted order by always inserting in a tree, right? Well, we could also sort it at the end, and then we also will have the n log n thing, right? But typically, we just sort it on the fly. Okay, and then once I'm done, I have this mini standard inverted index just for my current partition. I write it back to disk, and I'm done with this partition. Then I go to the next partition. I do it again and again and again for every partition. And I'm going to have a lot of standard inverted indices on my disk. Term IDs are gone. I don't have to maintain any mapping in memory. That's good. It gives me even more room in memory for storing my index. And at the end, what I have is my standard inverted indices on the disk, nicely stored, sorted by term, and then sorted by document ID on my disk. I took 3 here. Of course, in practice, it's going to be more. And I need to merge them. And now you probably see that, again, since it's already sorted, every index is already sorted by term and then by document. So it's going to be what algorithmic complexity to output my final index with everything sorted. Who says quadratic? Who says n log n, where n is the number of tokens or whatever? Who says linear? Yes, it is linear, absolutely. It is linear because this is, once again, the second part of my merge sort. So I just go through it, for example, all the yellows, that's it. I merge them. I can do it in memory term by term, right? Then the red, and so on, right? Yeah, and so on. The only reason I'm doing it in memory is to optimize the latency of the disk, because of course you could also do it document ID by document ID, but having to go on the disk document ID by document ID on parallel is going to be just huge latency that's going to slow you down, right? Who sees that? Right? You really have to use blocks. So this is the reason why we do it term by term in that case, and that's it. And now in linear time, just by maintaining these pointers that go through each one of the mini standard inverted indices, I'm outputting my final standard inverted index with all my postings and terms. Who understands SPIMI? More raise hands? Who understands that? Yeah, awesome. Great. So the complexity for the first step is T log m. M is the what we typically call the number of terms. We call it M. T is the number of tokens that I have positional tokens in my documents, and it's going to be T log m. The log m actually comes from the m log m for maintaining the dictionary sorted in every local index, right? So the m log n is for that. Whenever I insert in logarithmic time my term, so m log m, and then the T is because you have to go through all the partitions, and then the M is swallowed by the T, so you get a T log M. Then you have the second step, that is O of T, because as we said, it's linear in the size of the indices. Okay, so O of T, and overall it feels like O of T, and the reason it feels like O of T is that M is already very much smaller than T, and log of m even more so. So in fact, when you look at this, the log m is not really something you feel, right? So it's O of T. And we'll see in the next lecture, which I might start today actually, we'll see the relationship between T and m, because there is an empirical observation on how the number of unique terms in a document relates to the number of tokens. But that we'll see later when we are going to compress. So O of T log m for the first part, in which I do partition by partition and I build my local indices, and then linear for the second step when I merge them, and overall that gives the impression of O of T. That makes big data people very happy because linear time is great. This is also what you can parallelize well on clusters later on. And since I said clusters, I cannot resist to the temptation of showing you how we can now do it on a cluster of machines. So it's kind of a preview of big data. Who has ever heard of MapReduce? Who has never heard of MapReduce? Okay, so it's interesting how times are changing, because 10 years ago, when you would ask who knows MapReduce, almost everybody would raise their hands, because that was the ChatGPT of the time. Like MapReduce was this new technology invented by Google in order to basically index the web, right? That's how you build a web index. So I'm going to show it to you, how it's done, just on a high level, to give you an impression of how this is done. The issue that it addresses is when the collection does not even fit on your disk. Because for BSBI and SPIMI, I assume the collection was on your disk. You just were using the memory, which is much smaller than the disk, to build the index. But the collection fitted on the disk. Now, you agree the internet doesn't fit on your disk, right? You cannot just download the internet to your laptop. So you have to do it in a different way. And that different way is with data centers and clusters of machines. And this is exactly how Google, Yahoo, Bing, how they all actually do that. All right. So the idea, this is just a very high level. Of course, I'm not going to go with the same depth as I do in big data. I can come back next fall for that. So the idea is that queries that we want to execute, in that case, the query is for transforming the web into an index. I have the web, I want to download it and build an index. We can do it with a structure that looks like this. It's actually extraordinarily simple. I will explain what it does. But basically, this simple structure works on an incredible number of problems. It includes, for example, matrix multiplication, when you want to run machine learning on top of clusters and so on, and efficiently multiply matrices. You can use this as your core components to actually do it on large scales. And so the insight that they had back then at Google, it was more than 20 years ago now, is that you have 3 phases in what you do. In the first phase, which we call map, you process the data in parallel. So you have partitions of the data and you process each partition in parallel. In the second step, which is called shuffle, I like to call it spaghetti, actually, because this is where you have all the data flowing around in the cluster with an incredible mess, I might say. And then once we have shuffled the data all around the cluster, we have a second phase that is again in parallel, where it's called reduce, where we again execute that on every partition. And the trick, and that what makes it work, is the shuffling part, because the partitions you have here are not the same as the partitions you have there, because you shuffled all of these intermediate data points around in the middle. And so it's called map reduce. I wish it were called map shuffle reduce, because everybody forgets about the shuffle, even though that's the one that actually makes it complex. So it's just called map reduce by the people who talk about it. Okay, so I'm going to show it to you. Now, I would like to link it a little bit to BSBI and SPIMI, because there is a bit of a connection. I told you that this map phase, at first, executes in parallel on partition. We've already seen that. In BSBI and SPIMI, we already had partitions on the collection, right? That's where we process them. But there is a difference between BSBI and SPIMI on the one hand and MapReduce on the other hand. Is that for BSBI and SPIMI, that was on your laptop, on your machine, and the partitions were processed one after the other, sequentially. Partition 1, then you're done, then partition 2, then you're done. The difference here is that the partitions are not processed sequentially, they are processed at the same time on the cluster. Right? It's a bit of a simplification, we'll see next semester, but it's in parallel. So now you can have thousands of partitions that are processed in parallel, and this is much faster than doing them sequentially on your laptop. Who sees that? Right? It's the parallelism that's extremely powerful. The shuffling, of course, is the complex part, because then you ship data over the network cables of your data center to send the data where it should be. And then again, the reduce is going to be in parallel on the cluster. But in fact, I have a way that I like to explain this, what's going on. Why doesn't it want to show my slide? Let's see what's going on here. Ah, that's why. But yeah. So we are going to go and hunt Pokemons. That's the best possible way I can explain it. In fact, in big data, we do it really during the lecture. I'll bring the Pokemons and then we spend time hunting them. So here's how it works. I have all the Pokemons that I found in the last weekend, and I need to count them to know how many I caught of every sort. And I could do it alone, of course, on my own laptop, just counting them one by one and increasing my counters and so on. But the problem is that it takes a while because I have a lot of Pokemons. And then I thought, why don't I ask my students for help to count my Pokemons? Because we can do it much faster with several people. And so the trick, this is what I would like at the end. I would like my 10 Pokemons with a count, how many of each I have. And so what we can do to make it faster is that I prepared bags of Pokemons. These are my partitions of Pokemons, right? So I have bags of Pokemons, 10 of them. And I ask for volunteers, and I give to every volunteering student, 10 of them, one bag each of Pokemons. And they are going to process these bags. And you agree it's on parallel, right? They don't need to wait for each other. They just go to their seat and process these batches of Pokemons. So what are they going to do? They are called the mappers, right? It's the mapping phase. They are going to just take the Pokemons and write down on a piece of paper that I'm also giving to them how many they counted of each, right? So there's so and so many Pikachus and so on, right? 2 in that case. And so they write down these numbers for the batch that they received. Next, there is the reduce phase. And in the reduce phase, I will have, again, volunteers, different persons, who are each assigned one, maybe 2 to need less volunteers, right? But let's say 1 Pokemon to simplify. So let's say that this student is responsible for Pikachu. So what's going to happen is that she will get from every other student that did the mapping phase just the piece of paper corresponding to the Pikachu number pair, right? So what they do is you take scissors, right? When you have this piece of paper, and then you cut them, right? In between. And then that part is going to be handed over to the student responsible for Pikachu, and these others to the other students responsible for the other Pokemons, right? Now I have to add, this is a huge mess. The part where the students who mapped the Pokemons hand over the little pieces of paper to the students who reduce these lists is an enormous mess in the lecture. It takes a while to manage for everybody to hand on over their piece of paper to the right person, right? But after this is done, so that was the shuffling, after this is done, the person who is responsible for Pikachu receives all of this, and what does she do? Because we want to know the total count. What do you need to do? Sorry? Exactly, she counts, but it's all pre-counted, right? So in fact, she just needs to do the sum, right? So we do the sum of that, and that gives us the count, the total count of the Pokemons. That gives us 8, right? All right. And then we have our final summary. Typically takes us 20 minutes or so to do that in the lecture hall. Who understood? All right, awesome. Well, this is it. You know MapReduce. This is actually how it works. And it turns out that's exactly how we build a search engine to index the entire web. So now, instead of the Pokemons, I'm going to show you how it works with the collections and the postings and so on, right? But now you basically know the idea. So I have these documents. Now they are no longer stored on your laptop, right? They're actually stored on the internet, but we have a huge data center full of machines that can just download them, right? And so we start with that. huge connection, and we want to end up with this standard inverted index for the whole internet. So the way it starts, not surprisingly, we partition the internet, right? We just put it in partitions such that each partition can be processed by one process on one computer, right? So we build this partition of the internet, and then we have these mappers. So now it's not going to be my students anymore, it's going to be the computer in the data center. We have this batch of documents, and we are going to build, so I took an example with 2 documents, right? We are going to build the pairs of term documents, right? I don't need the term IDs because it's just, we could also, but the problem is that then you would need to synchronize the term IDs across the cluster, which is not easy to do. So let's just keep the terms. And all we need to do is output the terms together with the document IDs, right? And the document IDs, we can just generate them on the fly. There are ways to generate unique integers over a clusters, right? And so we output these pairs. So just like the Pokemon pairs, right? We had Pokemon number, and here we have term integer pairs, right? MapReduce loves pairs. It's pairs all over the place. So the input is pairs, even though to transform document into pairs, we just need to put some dummy value as either the key or the value, right? But it doesn't matter. And then we output these intermediate key value pairs. And then for the reducer, in the shuffling phase, we just need to make sure that all of the pairs that have the same key, so here the key is the term, that's the one on the left, so all the pairs that have the same term must end up on the same machine. So that's what the spaghetti does. It makes sure that we group all of the term document pairs with all the same terms on the same machines. And then the reducer can take these pairs of term documents grouped by term. So now we have all of them with information. And out of that, I'm going to build just the posting list for information, right? That is one for one term. And if everybody does that and all the reducers take care of every term, at the end, I will have the standard inverted index like this. Who agrees? Right? It's very powerful, right? And so the first use case was to download the internet and build the Google search engine. And Yahoo also at some point used that as well. That's how the Hadoop, actually the open source version of that came out. That was at Yahoo with dog cutting. All right. Oh, by the way, Jeff Dean, who is one of the engineers at Google behind all of these technologies, so HDFS, MapReduce, and so on, he will be at ETH mid-April, I think, April 14, and give a talk, just so that you know. Okay, so this is MapReduce. And the architecture, the way it looks like, is just we have this huge cluster of machines where we have one of the machines that kind of centralizes everything, and we have all of the machines that process everything. And when we download the internet, we store it on the machines. It's called the data nodes in here. And then we have the processes that take care of the MapReduce on the same machine. And we have basically all of this absolutely wonderful piece of technology that makes sure that we partition the data in the way we download it in exactly the way that it gives us the partitions. But you don't need to understand these details. Again, that was just to show you on a high level how MapReduce works. And next semester, we can spend 1 or 2 weeks on looking at the details of that. Any questions on that? For whom is that clear? Right, very good, very good. Okay, so I still have some time until the break. So now we have this huge index for the entire internet. It typically takes, I would say, 1 or 2 days to do that nowadays with the huge data centers we have. So if you want to index the whole internet, I would say 48 hours is a typical time. But there is a problem, because once you have downloaded the internet and indexed it, the internet has changed. There are new web pages, the content of the page has changed and so on. So what do? You do it all over again, right? So this is one of the issues. And this is what we call online index construction. Online is when the collection keeps changing while you index it, right? So that makes it just a tad bit more difficult. But this is real life because this is how the web is. People update the web constantly. So as you add new documents, let's say these are new web pages that got created, we could go naively for it and say, okay, maybe we just reconstruct the index, right? In fact, this is actually commonly done. You basically keep reconstructing the index on the fly, and there is typically these 48 hours indicative periods. Whenever you add a new page and you wait for it to be indexed, it was 48 hours. It might be that now it's become shorter, but back then 2 days was kind of the ballpark of the time that it took, right? So this is one technique. You just reconstruct the whole index periodically, and that we just refresh. Yeah, and then you keep adding the new postings. But there is a problem, is that staleness. So that's the idea that it's not instant. You have to wait for 48 hours or so until it's reconstructed. And typically, when you do that, so of course, it might not be the internet. It might be a company has their own database and they index it and so on. But while you do that, it might be that everything becomes slower because you're using all the computing power to build the index. And that's computing power that you're no longer using to serve the queries of the users, right? So it might be a bit slower. In fact, that's exactly the same thing happening to a relational database, right? When you build an index on a relational database, while you're doing that, it makes the database system slower to the users. So there are other solutions that people have come up with. One of them is the use of an auxiliary index. The idea is that the index of the whole collection that you've done a while ago, you just keep it and you don't touch it. And you just collect the updates and the edits to the collection in an additional index. That is much smaller, of course, because that one only contains the freshest updates. And that's what we call the auxiliary index. And so whenever somebody asks or is looking for a specific term, you just look at both places. You look at the very big index that contains the old internet in here at the bottom, plus you also check for the most fresh versions on the top. And you take the two together, and you basically give the union of that, right? All right. And what you can do is that at some point, once you have accumulated changes in memory in your auxiliary index, at some point, the auxiliary index is going to grow, right? And then it's going to get slower and slower and slower. So what you can do is periodically, you merge it back into the underlying big index, right? And then you start over with a new auxiliary index. So this is what you could do. Now, when you do that, you have to keep in mind that the index, so the one of the old internet, is so large that it's probably stored, distributed over plenty of machines in a cluster of machines. And you have to ask yourself, how do you organize this as files on a file system? Because in the end, you're going to have files. Whatever you store on a disk is made of files. And so there's a lot of interesting challenges to ask yourself. What is the granularity of a file? Do you want to create one file for every term? Do you want to create one file for, let me show here. Yeah. Do you want to create one file for every term? Do you want to create one file for the entire collection? Do you want something in the middle that you group several terms into one file and so on? And so this is one call that the engineers have to make. And typically, as you might have guessed, you need to aim somewhere in the middle, right? Because if you just have one file per term, then you have a lot of reading to do, especially the terms that have very small postings lists. It may be not very efficient to read. And of course, if you have just one file for the entire index, that's also not very efficient because you need to locate the things inside. And so it typically targets in the middle. But I think I jumped here. Yeah. All right. So what's nice is when you merge the auxiliary index into the big index, if all you do is add new postings list, is that you're just appending data, right? Because these are new document IDs. These are always higher integers. And so you just need one seek, so one access for every file, if every file corresponds to a term. But there is something you might be wondering, because here I was talking about new pages that got new document IDs with higher integers. But something else can happen on the internet, right? You could delete a page, right? What if a page gets deleted? So we cannot delete in the big index, right? Because that would be very resource consuming, right? We have to keep it how it is. And so here the trick, if a document gets deleted, we keep a list of documents with flags for every document, one flag for every document. It's called the bitmap, actually, just like these old drawing pieces of software, just a bitmap. And what happens is that we have one bit for every document. And when a document gets deleted, we just swap the flag here. We flip it, and we call it an invalidation bit vector. And basically, it's going to be filtered. Once you read it from the disk, you might find a result. But since it's been invalidated because the corresponding bit was marked, you exclude it from the results that you return. Right? Who is with me? Right? And so this is actually a very general principle nowadays, that when we delete things, what people commonly do is they don't actually delete it, they just mark it as deleted. In fact, if you use Git, Git does exactly the same, right? When you delete something in a revision, it's not actually deleting it, it's just creating a new revision that marks such and such document as deleted, right? All you do is keep creating new revisions as you go with Git. All right, so that's an invalidation bit vector or bitmap. Okay. So yes, one file is not practicable. So that's what I told you. One other reason why we cannot have one file per term is because the number of files would be huge, and this is much more than what technologies like Hadoop can process, right? So that's one other reason why we have to have files that have several terms to reduce the number of files. Okay. Now, when you actually do that, and you have your big index, you have your auxiliary indices, and you periodically merge back the auxiliary indices into the big index, you can look at it from a complexity viewpoint. So imagine that the size of the auxiliary index that triggers the merge is n, right? As soon as there's n postings in your auxiliary index, that triggers a merge. So imagine that we call T the number of incoming tokens here that will create the postings in there. So if I have n postings every time here, it's going to be T over n merges, right? It's just a division. So T over n times I'm going to merge every time n postings. And so the complexity for that merge, you remember, it's linear, right? When we merge, it's the second part of the merge sort. So if I have to merge n postings, the complexity is O of n. Then I have O of 2n, O of t, right? Again, it has to do with the fact that we append, right, to the posting list. So this is the complexity, and the overall complexity is the sum of all of that, right? So n plus 2n plus all over the way to t. So now if you write it down, it's O of n plus 2n plus t over n, because there's t over n merges, so you need to count from 1 to t over n times n, right? And that gives you t. Now, basically, we have to sum the first t over n numbers, right? 1 plus 2 plus 3 plus 4 plus all the way to t over n. Who knows the magic formula for that? I think you know it, right? You've learned it. The sum of the first n integers. What's the formula? Yes? Yes, so that's the generic formula for any such sequence. And in the particular case that it's plus 1 in between. So who heard of the n plus 1 over 2? Right? So your answer is absolutely correct. It's the generic formula for that even works when there's a gap that is not 1. And your formula, in the particular case that it's plus 1, the difference is plus 1, then that's n times n plus 1 over 2. But here we don't have n, we have t over n. So it's basically t over n times t over n plus 1 divided by 2. And that gives us the estimate of a complexity that is quadratic. Oh my, we hate that. Quadratic is a no-go. So that's absolutely not good. And we cannot do it like this, right? What we like in big data is linear, maybe, yes? Yeah.
Like memory, like just no memory anywhere because we're like storing the whole internet like 20 years ago.
Mm-hmm. So yes, absolutely. So let me get back to this consideration. There's actually several aspects to the deletion. So first, I'm going to argue that it doesn't matter, and then I'm going to argue that it matters, right? So the both of you. So if I wanted to argue it doesn't matter, then I would argue with the amount of data that gets created every year. And as a ballpark, you might have heard that basically what we create in 3 years corresponds to what we've created since the beginning of humankind, right? So one could make an argument, it doesn't matter because anyway, there is so much data that gets created, growing exponentially, that what was created 20 years ago is so small in comparison to what we have today that it doesn't matter. But now, we can also, of course, argue the other way around. And one way to argue is GDPR, data protection, right? You cannot just keep data forever. It's just the law, right? You have to, it's that the right to be forgiven in the EU and so on. So you cannot do that. And of course, another reason might be the costs. Maybe you're a smaller company, you cannot afford keeping everything. So what you can do is that when you merge, you can use the opportunity to delete, right? When you have a merge, you say, okay, by the way, since I'm merging anyway, let me just do a scan, pass through, and then remove what we need to remove, right? That also is gone over in detail in a technology called HBase that does that sort of things in big data. So also for the next semester. So there is a way to do the merge in such a way that you also get rid and prune old data that you no longer want efficiently. Yeah. Sometimes? Sometimes it does, absolutely. Yeah. For example, in Git, you can I can't remember how it's called. I think in Git, you can also flatten a history, right? If you have a huge history that you accumulated, and at some point you want to just prune it and so on, you can just flatten it back to a single revision, right? And here it's really practical purposes, like either you're obligated by law to delete, or you want to save some space. Yeah. Mm-hmm. You're welcome. Squash, yes, exactly, squash. Squash, SH or TCH? Squash, yes, squashing. Yeah, so that basically does that. It removes all the things that got deleted. Yeah. All right, but the main point is you just don't delete it every time. You just accumulate the deletes, and then periodically you get rid of them. Okay. We're soon at the break, so maybe. So I gave you the calculus. So I'm going to end here because that's a great, it's like in a Netflix series, right? We have this huge end of the episode, like mystery, what's going to happen next. So of course we have a solution for this. We are not going to stay with something quadratic, and you will see that solution after the break. So see you in 15 minutes.